So that is the difference why we get stuck when components are made out of ferrous and unferrous, especially aircraft with aluminum. We cannot afford to have things penalty. So that's where you get stuck there. And if you see now coming to the fiber reinforced plate is a composite, you have a SN curve like far away above the steel and all. This y-axis can be stress, amplitude, range as max with number of cycles to failure. And this is a very idealistic slope you'll have, but if you recall who are working in the composite, the design philosophy of metallic structure and composite is different. While the metallic structure is based on the strength, stress based, while the composite is based on the strain based, because composite has have a fiber, resin, orientation, layer. So you cannot maintain same stress in homogeneous metal in aluminum or steel. That's why the strain based. So usually if you want to refer any SN curve for stress versus number of cycles for composite material, it will be mostly horizontal. So always it is plotted with strain versus number of cycles to failure for the composite. That's the difference there. And when it comes to your vibration, obviously the loadings are not in the stress, strain, and it is mostly in PST, power spectral density, which is d square per hertz. So unlike in metal, if you do the testing, cyclic testing, it will fail into two parts, but in composite it will not fail. So the usual benchmark is, before starting the test, you take what is the stiffness, deflection per unit load, and keep on cycling it till you get 2% decrease in the stiffness, will known as the failure. So that way you define your curve for the composite. And anyway, composite is known to be good resistance for the fatigue. So nobody bothers about fatigue and tensile or thing. Only it is a concern when it is subjected to compressor load with impact loading, which may induce some delamination, so on and so forth. So now let us define.
Why only 2% for that composite?
No, that is a standard. 2%, if a decrease in 2% stiffness is considered as a failure. In unlike in metal where it fails during repeated loading into two pieces, here you will not find the failure like that. So this is a standard practice is to take as a 2%.
So regardless of, the composites are 100 different varieties, right? So
yeah.
2%.
That's why you have to test. Unlike SN curve 2000 aluminum means you can roughly consider same, but in composite, if system is different, you might have using same resin, same fiber, but you have a different layer or orientation. That's it. You cannot use same SN curve for that. You have to generate every time. Unless you use a standard resin and fiber, which is open literature is available, you can make use of that. But for designing any structure based on meeting certain requirement, where you have to have a ABD matrix to answer something, and you have a number of layers and orientation, it may be symmetric, asymmetric, and in that case you cannot use a common SN curve available in the literature. It has to be generated for that particular system. Now, what are the salient features of SN curve? See, when it is y-axis, x-axis is number of cycles to failure, 1 to 0 means 1 cycle, 10 to the power 0 is 1 cycle. Then if you go to the true fracture strength, the failure will occur. We are not referring to the ultimate strength. This is a true fracture strength. If you recollect, you have two types of stress strength curve. One is called engineering stress strength curve, another is true stress strength curve. As you know, the engineering stress strength curve is lesser than true stress strength, but that is a conservative way of doing it. But in the case of the failure when it occurs, it will go to true fracture strength where your necking takes place. Then if you do another specimen with lesser stress, it will take more number of cycles to failure. When it comes to yield point, then where you have plasticity, beyond any yield, you will have a plasticity. And of course, this is for ferrous material. You come to somewhere, of course, showing 10 to the 7, doesn't matter, but benchmark is 10 to the 6. There's no issue. So endurance limit below which you will have a infinite life. Sorry, I have
Mhm.
missed on. So there is a 1 to 10 to 3 is known as low cycle fatigue, where too much plasticity. So in aircraft structure, we don't consider any low cycle fatigue unless except it is an engine. Even engine also some parts are analyzed for high cycle fatigue, low cycle because you have a high centrifugal force, then you have a temperature in turbine area, hot region, and all. Obviously, some of them will undergoing the plasticity, or even automobile, high ductile material. So those are low cycle. But in aircraft structure is always high cycle fatigue, which is within elastic limit. And limit is
Hi,
unlimited
sir.
beyond. Yeah.
Sir, I have one doubt.
Mm,
Sir, if I have to design for steel, there will be endurance limit will be infinite.
correct.
So that time we have to use ultimate like yield strength or fatigue strength only for design.
No, no. If you know endurance limit the material, that's it. No, I mean you have to. You don't want
But
any
it will be
failure.
infinite.
Infinite light means your stress level has to be less than the endurance limit.
Okay, sir.
Of course, this is idealistic. Now, in automobile they put engine accelerate from 0 to 5 seconds, so and so. But this is what? This is test bed condition, right? This is a, but when the structure is exposed to environment, it undergoes so many machining process and all. I will get to know why it is important to know the factors that affects endurance limit. Okay, this is the endurance limit is that during testing. But when you make a component from the same material, it undergoes so many processes, chemical process,
Okay,
then technology process, then machining and all. So that affect the endurance limit.
okay, sir.
So this life has been used for the last more than 100 years, and as long as your loads are within elastic limit, and is used in design application where the upright stress is primarily within the elastic range of material, and the stress life method doesn't work well in low cycle fatigue. See, that is if by any chance if you have got a strain life curve, SN curve, you can use for high cycle fatigue because both are matching together, but you cannot extrapolate from the high cycle SN curve to the low cycle fatigue because in low cycle fatigue you have a plasticity. Now it brings to three regions. One is a low cycle fatigue, that red color and yellow and green. This is again linear versus log scale. The first domain is characterized as a large number of plasticity, is low number of cycle, and the second one is flexibility 10 to the 3 to 10 to the 6 cycle. It corresponds to the aeronautical applications, and the third one is the unlimited fatigue. Below certain, that you will have an infinite life.